Hey, welcome to section 2-5. We're going to talk about measures of position today. So the first is it's going to feel like a throwback to the beginning of chapter 2 when we talked about graphs, because this is going to be a way to display data. So let's start with a data set. What we're going to do is we're going to make a box and whisker plot. Funny name. And let's start with a data set. And if you want to, as I'm writing this out, you can enter this in a list in your calculator and follow along. I'll remind you how to do that in a minute. If you need help, we're going to do 12, 27, 35, 75, 10, 19, 25, 34, 34, 37, 30, 31, 25, 29, 20, 17, 18, 22, 24, 31, and that's it. Okay, so that's going to be our data set. So you want to enter that in your list. So as a quick review, if you're on TI, you're going to hit Stat. You're going to choose Edit. When L1 comes up, you're going to use your arrow buttons to highlight L1, and then you're going to hit Clear and the down button. That's going to clear out that list. And then you're going to put your numbers in your list, no commas, just hit your number and then hit Enter and keep going all the way down. On your class calc, you're going to come over here and remember you need to name the list. So I've named my list A right here, as you can see. I'm going to tap and hold the 7 to get my A, and then equals. And remember, you have to use square brackets for a list. So you're going to tap hold these parentheses, and you will want commas in between your numbers. The comma is below the 1. So once you have that list entered, the way that a box and whisker plot works is it's going to plot your minimum on a number line. We're going to plot the minimum, what we call quartile 1, the median, quartile 3, and the max. MAK, MAX. All right. So this is what we call our 5-number summary. That's kind of the general name for this set of numbers. So if your homework asks for the 5-number summary, it's looking for these 5 numbers. Now let's talk about what Q1, Q3 are. What this stands for is quartile 1, and this stands for quartile 3. So basically what this is this is the median of the first half of data. And this is the median of the second half of the data. Now, remember, that's assuming your data is in order, which this is not. So you would need to sort this. So basically, you're taking your whole set of numbers, you're finding the middle, that's your median. Then you're finding the middle of the first half and the middle of the second half. You're dividing it into quarters, which, by the way, is one of the characteristics of this is that the first quarter of data is between the min and quartile 1, the next quarter, quartile 1 median, and so forth. So it's dividing everything into quarters. Once you get those numbers, then we're going to plot them on a number line. So let's first calculate those numbers. If you recall on a TI, you're going to go back into and click Stat. But now instead of Edit, you're going to go to Calculate, and you're going to hit 1 var stat. And when it clicks you over to the home page, you're going to tell it that you want list 1 for your 1 var stat. And then you're going to scroll down, you're going to find your, at the bottom, it'll say, it'll have this huge list of numbers, mean, sum of the X's, all that stuff. As you scroll down, it'll say, minimum, quartile 1, median, quartile 3, and max at the very end of that list. And that's your 5-number summary. Okay, on class calc, you come over here and you've got your list entered. If you come down here, there's a couple ways to get information. One is you can go to stat, and what we did manually before is like, here's your median, here's your min, and here's your max. You can calculate some of those values there. But the ClassCalc does it all in one place as well. If you hit distribution and plot and come down here to box plot, that's a box and whisker. So if you hit that, it's going to ask you what list you want to use for your box plot, because again, you can have multiple lists going. And so I'm going to tap and hold the 7 so that the A comes up, and you can see right there the box plot comes up, so it draws it for you, and you're just going to copy that on your page. Now, sometimes when you do that, when you hit box plot, you can't see it. That's because it's somewhere else in your screen. Like maybe you're zoomed in over here and the box plot's over here. So it's just like your phone or any other touch screen. You can zoom out and zoom in like this, and you can move the graph one way or another until you see it. So I'm going to do that, okay, and show you how that looks. You can zoom way out, you can zoom way in, you can slide to the left or right, that kind of thing, until you see where that box plot is. If you want the numbers for this box plot, you're going to come over here and you're going to hit this quartiles button, and it's going to give you your 5-number summary. So you've got quartile 1, quartile 3, here's your min, your max, and your median. So if you need to write those down, and you're going to want to graph those accurately. Okay, so let's do this. So our min is 10 and our quartile 1 is 19.5. So on your graph, when you do your box plot, you're going to want to start with a number line. The number line is important because you want your box and whisker plot to be to scale. And again, you're going to need to decide how to break this up. If you've got a big range, you're going to want to count by 5s or 10s, maybe even 20s. If you've got a small range, then maybe you want to count by 1s. The goal is to not cram it all together, and then not to have this huge number line. So you kind of choose appropriately. So I see that I'm going from, my min is 10 and my max is 75. So I'm thinking that maybe I'll count by 10s, 5s would probably be fine too for now, just because my number lines, I don't know, maybe I'll go by 5s. So let's start down here. This is going to be 10, 15, 20. I'm just going to label every other one. This is 30. This is 40, 50, 60, and 70. It's kind of nice if it's spread out enough so you can kind of see what's going on. You're not estimating every value. So I've got a minimum at 10. What you're going to want to do is just put a little hash mark at 10. And my maximum is 75. So I'm going to want to put a little hash mark at 75 there. And then we're going to mark out the quartile 1, median, and quartile 3. So let's go back and grab those numbers. So quartile 1 is 19.5. 26, and then 32.5, 19.5 here, 26 here, and I can't remember, 32.5. And so roughly there, say. And those 3 values you form a box around. Okay, that's your box. And then you form lines out to your min and max. Those are your whiskers. So this is what a box and whisker plot looks like. All right, a little bit of vocab here. Interquartile range. That is the length of the box. Okay, so that's going to be from here to here, whatever that distance is. So for us, we're going to our 5-number summary because we want to look at those values exactly. And I'm going to take quartile 3, which is 32.5, and I'm going to subtract quartile 1, which is 19.5, and I get a span of 13. So that's what my interquartile range is. And there's an abbreviation for that. We abbreviate it IQR. So if your homework says, what's the IQR? That is the box length. And so you'd say that's going to be 13. All right, now, advantages of this distribution. First of all, it's a really easy way to see where the data is, and we've got some rules for it, and I'm going to write those in right here so that you can have a reference. 25% of the data is in the first whisker right there. The next 25% of the data is in the first half of the box. The second half of the box is the next 25%, and the last whisker is the third 25%. Now, what does this tell us? It tells us the shorter that little span is right here, like this little span, the more concentrated the data in that area. So for example, if you compare, let me grab a different color here. If you compare this little piece to this piece, so each of those pieces has 25% of the data, but in the box part, it's squashed into this little tiny piece, and in the whisker, it's spread all out. What's that mean? It means that there's probably outliers, okay? And the data is dispersed through that area. It's not as concentrated. So if we were drawing a histogram, the histogram would be way steeper where that box is, and it would peter out where that right-hand tail is. So if you're talking about like, is this distribution skewed or symmetric? I would say this data is skewed, and it's skewed right because it's got a long tail on the right and it's got a high concentration of data on the left. Like if I was to estimate what the histogram looks like, it would be like, it would have a huge amount of data here, and then it would kind of like do this, right? You'd have some small little bars out here, but it'd have high bars here. And if you remember from our symmetric pictures, wherever the tail is how it's skewed. So this would be data would be skewed right. So it gives you an idea of how that's proportioned. It also tells you obviously that you probably have an outlier. That 75 value is probably an outlier. And so you can gather a lot of information there. So some of your homework questions can be based off these percentages. Like I could say, what can you tell me about the values roughly from like 20 to 30? And you could say, well, I can tell you that 50% of the data is between those values, because that's the range of the boxes box there. Some questions like that can come up. So that's the interquartile range. Now, the other thing that we'd like to be able to calculate from this graph is what an outlier is. Okay, and there's a little formula. Don't be afraid of it. It's a little mathy, but I'll walk you through it. So the way that we define an outlier on a box and whisker plot. Now, remember, we talked about this in a normal distribution. Last time we said more than 2 standard deviations away from the mean is an outlier. That's what we do when we know the standard deviation. But as you may have noticed here, we didn't calculate the standard deviation of this data. So yes, you could calculate that, and then outliers would be considered 2 standard deviations away from the mean. But to avoid having to calculate a different value like standard deviation, we've defined what an outlier is in terms of this box chart. Okay, and so the formula is an outlier is going to be more than, that means bigger than, okay, to the right of, depending on how your brain works, more than, whoops, not that, more than quartile 3 plus 1.5 times the interquartile range, okay, or less than quartile 1 minus 1.5 in interquartile range. All right, so let's walk through these formulas so they're a little bit less scary. Let's take first the first equation, quartile 3 plus 1.5 interquartile range. So quartile 3 is right here. Okay, it's the top edge of the box. And if you jump back to your calculator, you can remind yourself that, okay, quartile 3 is 32.5. So that's 32.5. We'll just put that there for reference. So if I take quartile, let me do this. let's copy this and paste it over here. So I'm working on this formula. So quartile 3 is 32.5. Then I'm going to say plus 1.5 times the interquartile range. And that's the length of the box. And we calculated that just a minute ago. It's 13. Okay, so again, your calculators do order of operations for you. All you need to do is type the numbers in just like you see them there. The calculator will crank out a value for you. So I'm going to go 32.5 plus 1.5 times 13. And I get a weird glitch in my calculator. Hold on, let me do it again. Plus 1.5 times 13, 52. Okay, so let's go up here on our picture and look where 52 is. That's like, say, right here. So what this is saying is anything more than that number. So anything from here up is considered an outlier. All right, I'm gonna brighten that up a little bit so you can see it better. Outlier, anything from here up, okay? Now let's calculate the low end, because remember, outliers can be any point on either side of the median as long as they're far enough away. So it's like in our normal distribution that we looked at the other day, it's the tails, okay? So you've got a little range on the top and a little range on the bottom. So on the bottom, we're using this formula. Right here. And so we're going to plug in these values. So first, quartile 1, that's going to be right here, 19.5 minus 1.5 times the interquartile range, which is still 13. So on my calculator, I'm going to go 19.5 minus 1.5 times 13, and I get 0. Okay, so that's a little atypical, but here's what's happening. So because the box is so far to the left, that means that the mean is also very far to the left. So you're not going to have any outliers on the left because all of the left-hand data is going to be super close to the mean, and it's not going to be that far away. This is not a symmetric distribution like we talked about yesterday. It's skewed. So this is saying, well, the outliers on the other side are going to be, here's 0, right? They're going to be here. Well, we don't have any data points there, so there's no outliers on the left, but there will be possibly on the right. Okay, but that's our range. So your left-hand range and your right-hand range can be on the graph or off the graph. It doesn't matter. You'll still have both, but being off the graph eliminates that as an option. Okay, so now I can go up to my data and say, well, I'm looking for any data values over 52 or under 0. Now, obviously, we don't have any under 0, but over 52, I've got this value, and I think that's it. Everything else is 20s and 30s. So that means that this data point is an outlier. So that's how you figure out how many there are and what they are. You can have more than one, you can have lots of them. Okay, it might be that there's a bunch of points in that span on the right or a span on the left, and you just go through all your data points and evaluate it. Okay, so that is how you do a box and whisker plot. Next thing we're going to talk about is finding a percentile. So I'm going to use this same data set and just erase what we've done here and use this spot. All right, so a percentile, you may have encountered percentiles before. I have often encountered them like in the medical community. So for example, if I take my son into the pediatrician when he's little and they measure him and they say, oh, he's in the 95th percentile for height. Or the other place that we often hear them is in standardized tests. You know, you take the SAT exam and you're like, you're in the 75th percentile. So what that means is whatever the number is, let's take the 75th percentile. If you are in the 75th percentile, it means that 75% of the population in that scenario is below you and 25% is above. So it places you in the span. If you think about it as a number line, like here's 0% and here's 100%. When I give you a percentile, it places you in that range. So if you're the 75th percentile, that means that there's this many people below you and this many people above you. Okay, so sometimes we like to be able to tell where a number is in relation to the other numbers. That's why this section is called measure of position, because it's like, where are all of these numbers? Are they outliers? Are they in the 50th percentile? If I'm in the 50th percentile, it means I'm right in the middle. I'm really close. You know, I'm right in that average spot. If I'm in the 90th percentile, it means I'm probably unusual, right? Like I'm way taller or had a way higher score than most people. Or if I'm in the 10th percentile, it means I'm way shorter or scored way lower than most people, that kind of thing. So we can kind of tell where a data point is in relation to the other points. The way that you find a percentile is you're going to take, I'm going to write it in formula form. You're going to take the number of data entries less than your entry, and you're going to divide it by the total number of data entries. So let's take a look at our data set. The first thing that you need to do is put it in order. So let's remember how to do that. You're going to, on class calc, you're going to hit stat, and then you're going to hit this sort, and we're sorting list A. Okay. And then that's going to give me a list in order. We're going to jump back and use this list to point at. On your TI, where we go? Here, you're going to hit stat. And your first option when you hit stat under edit is going to be edit and then sort A. And then you're going to hit that, and then you're going to tell it that you want to hit list 1. So you're going second 1, and that will sort your list for you so you can look at it in order. If it's not in order, you're going to get a wrong answer. So let's say for this, I want to know, let's take the number 22. I want to know what percentile is this data value in? Okay, so that's what the question would say. What percentile is 22? So I'm going to go over to my sorted list, either on a class calc or the TI, and I'm going to find 22. It's right there between 20 and 24. And I'm going to count the number of data values below it, not including 22, strictly below it. So I'm going to start at 10. I'm going to count 1, 2, 3, 4, 5, 6 values below 22. Okay, so I'm going to take 6 values. That's the number of data entries less than your entry. And then I'm going to divide it by the total number of data entries. I think we had 20 points. Let me check that. Yeah, we have 20 total points. So I'm going to take 6 divided by 20, and a percentile wants to be in percentage form. The way you go from fraction form to percent is you divide the two, first of all, 6 divided by 20, and that's going to give you a decimal. So when I divide that out, I get 0.3. And then you take that decimal, and to turn it into a percentage, you move the decimal 2 to the right. So I'm going to take this and move it 1, 2 to the right. Now, there's not a number there. So if there's not a number, a 0 holds the place. So this is going to be 30%. So that means that the data point of 22 is in the 30th percentile. That means that 30% of the values are below it and 70% of them are above it. Okay. And then the last measure of position is related to the normal, the symmetric normal distribution that we talked about last class period. So let's draw this out. Remember, this is like a smooth curve representing a histogram of sorts, right? It's how much data. So there's a lot of data in the middle, not very much on the sides. The mean is in the middle. And then we have standard deviations marching away from there. So this is going to be the middle plus 1 standard deviation. This is going to be the middle plus 2 standard deviations, and so forth. And the same happens the other way. This is going to be the mean minus and the mean minus 2. Okay, so that's our distribution. Now, when we take a data set and put it, and it's normally distributed like this, it's symmetric curve. The data set can look a lot of different ways. If we're measuring temperatures, say, you could have positive or negative numbers. They could range from, I don't know, minus 32 to 110. Okay. If you're measuring weights of something, you're not going to have negative numbers. It's going to be from 0 to something. If you're measuring how many naps you take per day, you're going to have rather small numbers. If you're measuring the number of calories you eat in a day, you're going to be in the thousands. So what you're measuring dictates what your numbers look like, right? So I could have a normal distribution, and I could have numbers that are like 0, 4, 8, -4, -8. I could have a distribution that looks like this, or I could have a distribution that looks like 1257, 1352, like huge numbers like that. And you don't know what's going on with those numbers unless you understand the context of the problem. So one thing that we do is we kind of standardize these values, and the standardization of these values is called a z-score. And there's a formula for this. This, as far as I know, is not a button on your calculator. So this formula, you're actually going to need to write down, kind of like that outlier for your box plot, and be able to calculate this. The formula is x minus mu over sigma. So let's review notation. X is going to be your data point, the data point that you want to standardize. Mu is your population mean, and sigma is your population standard deviation. So you need to know all those points of information. Now, where do you get those points? I could give you a data set and you could calculate the mean and the standard deviation on your calculator. We've talked about how to do that before. I also could just tell you what the mean and standard deviation is, which was what I'm going to do in this example. So I'm going to say if the mean calorie intake of a United States woman is 1,500 calories with, let's say, a standard deviation of 20. Find the z-score for a diet of 1,472 calories. Okay. All right, so let's do this. Here's our formula that we're going to use. The first is your data point that you're interested in, the data point that you want to find the z-score for. That's going to be 1472. Then you're going to subtract the population mean. That's 1,500 calories. And then you're going to divide by the standard deviation. The standard deviation is 20. Okay, now, when you are doing this calculation, when we do division with a long bar like this, there's a hiccup with the TIs. Okay, if you just type in 1472 minus 1,500 divided by 20, that your calculator will only divide the 1,500 by 20. So the rule is when you're doing division with this long bar, you have to put parentheses around either the top or the bottom if there's an operation going on. Now you can also put parentheses around the 20, it doesn't matter. So if you want to, you just go, okay, when I'm doing division, I always put parentheses around the top, parentheses around the bottom, that will always work. But really it's only necessary if you're doing a calculation. Okay, now watch what happens on, actually I'm going to calculate this number really quickly. 1472 minus 1,500 divided by 20, and I get negative 1.4. Now I'm going to draw you a picture in a second and explain what that means. But let's jump over to Class Calc and look at how this handles the calculation. So I'm going to come down here and I'm going to do 1472 minus 1,500 divided by 20. Do you see what this looks like here? That's what the TI is doing. It's calculating it like that because all it understands is you want to divide that 1,500 by 20. Now, if you take, let's back up and delete this, and you take that computation and put it in parentheses. So your parentheses again are right here, not brackets. So the brackets are only for the list. The parentheses are for calculation. And now you hit divide by 20. Look at what that looks like. The whole thing's divided by 20, which is what you want. Okay. So that's a visual of what the TI is doing. It just isn't showing you that. So negative 1.4 is your z-score. Now, what does this mean? So if I draw a picture of my information, here's my symmetric distribution for this problem. We're assuming that these are symmetric distributions. Z-scores only work for that. The mean is 1,500 and the standard deviation is 20. So that means my first mark here is 1,520. My second mark is 1,540. And remember, the empirical rule is going to say 34% of the data is between these two numbers right here. Okay, and then another 13.5 between these two numbers. And then I can do the same thing in the other direction. I'm going to subtract 20. So this is going to be 1480 and subtract 20 more. This is going to be 1460. Okay. So that's what that distribution looks like. And the question is, here's 1472. Let's mark that on here. This is just a number line. 1472 is roughly right here. Let me get a brighter blue. Hold on. Right here. This is 1472. Somewhere between 1460, 1480. And you can see that this is one standard deviation away from the mean, and this is 2, right? So it's between 1 and 2 standard deviations to the left of the mean. Now, what do the z-scores do? They take this whole distribution. This is just a number line down here. This whole thing's this is a number line. And we're way up here in 1,400 to 1,500. The z-scores just slide that distribution all the way down, and they slide it down so that 0 is in the middle. That was a horrible drawing, but I'm gonna try to do that better. Here we go. I don't know if that's better. It's the same. I know it looks skinnier, but it's just my drawing skills, but it's the same distribution. It's just slid down so that 0 is, I cannot handle it. I can't handle it. I'm sorry. Okay. I don't know. That's not any better. I don't know what's wrong with me today. Okay. So that's your distribution. 0's in the middle. And in this standardized curve, 1 is the standard deviation now, and -1 on the other side. So it takes all of these values and it pulls them down and it puts them with 0 at the middle. Now, what's our z-score? Our z-score is -1.5. Let's put this on our new number scale. If this is, I've got -2 and this is 2, where's -1.4? It's right about here. Now look at where it is in relation. It's the same distance away from the middle. Here's 0, our new mean. This is 1 standard deviation away, and this is 2 standard deviations away, right? So it's 1 and a little bit. Well, look at this value over here, this blue value, 1472. It's in the same place positionally. But what we've done is we've just kind of normalized the score. So now instead of waiting through 1400, 1500, what does that mean? I can look at a z-score and say, this z-score right here, what it tells me is how many standard deviations away it is from the mean. Since the standard deviation is now 1, the standard deviation on this new curve is 1, and the mean is 0. That standard deviation of 1 allows my z-score to tell me exactly how far it is from the mean. So if you talk to me about this number 1472, I can't tell you off the top of my head anything about it positionally. I could say, I mean, I can obviously see that it's less than the mean, but I don't really know exactly where it is. But if you tell me that the z-score is -1.4, I can say, hey, that's -1.4 standard deviations to the left of the mean because it's negative. These are negative numbers. These are positive numbers. So it's under the mean. It's exactly 1.4 standard deviations away. So it's a typical score, right? It's not an outlier because it's not more than 2 standard deviations away. And so that's the advantage of a z-score. It just allows us to normalize. So like, let's do a different scenario as an example. If I tell you that my blood pressure, well, I don't even know typical scores for blood pressure. Let's say if I tell you that my vertical jump height is 10 inches. Okay, that's wishful thinking, but let's say it is. Okay, I mean, I don't know. I don't know what it is, but it's probably not that. You can't tell me anything about that. But if I tell you that my vertical jump height has a z-score of -2.3, then you can say, oh, you're on the low end of things. You're an outlier. You're unusually low, right? Because that's 2.3 standard deviations away from the mean. And anything less than 2 is an outlier. So you're like, you need to go to the gym and work on your vertical jump. Okay. So that's the advantage of the z-score, is you can immediately look at it and tell me something about the position. So again, the z-score is a standardization of your value, and it tells you how many standard deviations away your value is from the mean just by that number. If it's negative, it's under. If it's positive, it's above. It can be either or. Okay, so that means that the order that you subtract these in is very important, because that's going to give you your positive or negative value. It's always your value that you're looking at minus the mean in that order. So that is the end of our measures of position. I will talk to you later. Good luck and see you soon.